pretty self-explanatory.
There's an underlying assumption that you are.
And
good.
the assumption is one fact. So just,
Well, then it's not an assumption, it's fact. I guess his assumption is he's great.
who are you teaching calculus to?
What's that?
I said, who are you teaching this to?
No, that's not calculus. It's,
No,
I'm
you
forced to
haven't.
use yellow chalk.
That's right, you haven't. I went to class, I forgot about
I wish I could.
that.
I'm forced to use yellow chalk.
I thought that was saved for the wage, for the calculus was.
It is, but I'm out of white chalk, so I'm forced to use yellow chalk.
Dire times.
So let's begin with that. Name the Father, Son, and Holy Spirit. Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. All right, so. Tradition has it that Luke was adopted the position.
Yeah, I used the restroom.
Yes, you may. All right, matrix arithmetic. So yesterday, or whenever it was, yesterday, I guess, right? We talked about what a matrix is. Matrix. A, and it's little a I sub j, where I goes from 1 to m, and j goes from 1 to n, and this is, m is the number of rows, and n is the number of columns. Alright, so A is a m by n matrix. What's that? No. Why? So you should take time away from this class and finish another class's quiz?
No, your quiz. I let you know.
Oh, I wasn't aware you were gonna finish it. You handed it in, why should I give you more time?
I left in the middle, like literally 10 minutes in.
Alright, well, we'll do it some other time. Fair enough. So we got this matrix, right? And we were talking about doing arithmetic on it. So we talked about addition. So if you got A plus B or A minus B, it doesn't matter. The conditions for the two matrices are the same. It's that the conditions are that the two matrices must be of the same dimensions, right? So they must have the same number of rows as they do the same number of columns. And what that means is, well, the reason for that is because when you do addition and subtraction, you add corresponding elements together. So if there were different number of rows or different number of columns in either of those two matrices, you couldn't add element to element together because one matrix would have either more or less elements, and that therefore can't do it. And of course, this is any number of matrices that you want. It's not just limited to 2. You can do any number, just like you can add any number of real numbers together, any number of matrices together. And the condition is the same for all of them, that they all have to be the same dimension, right? So matrix addition and subtraction is pretty straightforward. The other operation we talked about was scale of multiplication. and that is just multiplying every number, every element in the matrix by that number. And I don't know if I mentioned it in this class, but you could also go in reverse. So for example, if you have, I don't know, 5, 10, 20, -5, 5, 50 as that matrix, and you notice that there's a common factor of 5 in each of those elements. So you could factor that out to be 5 times 1, 2, 4, -1, 1, 10. Right? So you can go in reverse with scalar multiplication if it's possible. I guess you could factor anything out, but then you'll end up with some fractions and stuff. But when it's obvious, you can turn it into this, and that's actually not a bad thing to look for, because as we'll see, it's much easier to deal with a matrix like that than that, only because of the magnitude of the numbers and stuff like that. Right? But so this is addition and subtraction, and this is scalar multiplication. Right. Now we come to the hard part. Not hard, but it's little not really. And that's matrix multiplication. Alright, so if we got A, and we're multiplying it, right? The conditions here are as follows. So assume A is a M by P matrix. Right? That means it has M rows, P columns. In order for you to be able to do matrix multiplication, this must be a P by N matrix. Right? M and N do not need to be the same. They could be the same, but they're not related in this way at all. What is a requirement, however, is this P be the same. So in other words, the number of columns in the first matrix must equal the number of rows in the second matrix. That is the only possible way you could do matrix multiplication. Right? If that condition's not met, you cannot do matrix multiplication. Question, Luke?
Yeah. I'm sorry, is the first one M or N?
M.
So they're both M, or is it one N?
No, this is M, that's N.
Thank you.
That's what I said, writing this, I don't like using M and M because it's hard to distinguish. For me, I would prefer to use this and this. Then there's no, but traditionally they're lowercase, but. So the idea here is that the number of columns in the first matrix must equal the number of rows in the second. Again, that is the only way that you can do matrix multiplication. If that condition is not met, you cannot do the multiplication. If it is met, then you're going to end up with an M by N matrix as the dimension of the product. So this is equal to C, and C will be an M by N. A must be this, B must be that. So that's what you're going to end up with. Now, again, it's okay if M and N are the same. That's fine. They don't have to be the same. It's fine if all 4 of those numbers are the same. Right? Doesn't matter. The only thing that matters is that this P and that P are the same number. So for example, if A is a 2 by 3 and B is a 2 by 3, Could I perform this operation? Yes, because they're the same dimension, right? Can I perform this operation? No, because A is a 2 by 3, and that's getting multiplied to a 2 by 3. So this 3 and this 2 are not the same, therefore we cannot do matrix multiplication. If this was if A was a 2 by 2, can I do the arithmetic? Can I do the addition? No, because they're not the same dimension. Could I do the multiplication? This is a 2 by 2. Yes, what dimension would I end up with?
2 by 3.
2 by 3. Okay. So that is pretty straightforward. Again, the P's have to be equal to each other, but what that's saying is the number of columns of the first matrix must equal the number of rows of the second matrix. And the dimension of the product is the number of rows in the first by the number of columns in the second. So that's how matrix multiplication is organized in terms of requirements and such. So then the next question obviously becomes, how do you do that? Well, before we answer that definitively, let's just define two other matrices first. And that'll help this along a little bit, I think. So they are what are commonly known as vectors. If anybody is or has taken physics or something, you are quite familiar with that term, I suppose. However, it's in a little bit different context. A vector is like a force is a vector, right? And a vector has two components. It has a magnitude and it has a direction and such. But you kind of use it differently, but the same. But anyway, within our context here, a vector is a one-dimensional matrix. So it is a matrix, but it just has one dimension. So that gives us two types. Then we have what we call a row vector, and we have a column vector. Right? So a row vector would look something like this. Here's our matrix: 1, 2, 3, 4. It just has one row. So this is a 1 by 4 matrix. Right? And it truly is a matrix, but since it's one-dimensional, it's called a vector. And a column vector, you could guess, would be 1, 2, 3, make it different. So this is a 3 by 1 matrix. 3 rows, 1 column. So we call this a column matrix. We call this a row. Call this a column vector. This a row vector. And that's just to be consistent with the sciences and such like that. Like I said, force, for example, is a vector, but in physics, vector takes on a little bit different meaning in the sense that it has two components. It has a direction and it has a magnitude. The magnitude of a vector is nothing more than the dot product. Anyway, we'll talk about some of that stuff. So these are